Hello again. Welcome to tutorial number 9, where we shall be dealing with questions under the topic properties of matter. Okay, so here we are simply going to be applying those concepts in solving a few simple questions, and I'll just take you through on how you actually have to go about some of the questions. Okay, so let's look at question 1. We have a force of 20 newtons being applied to the ends of a wire 4 meters long and produces an extension of 0.24 millimeters. If the diameter of the wire is 2 millimeters, calculate the stress on the wire, its strain, and the value of the Young's modulus. Okay, so we want to find the stress, the strain, as well as the Young modulus. So the first thing here you have to do, make sure all the units, all the quantities have standard units. We have the radius, or rather the diameter, in millimeters. The extension is also in millimeters, so we have to convert these values to meters. Okay, so now we proceed. We know that stress is given as force over area, okay, where our area is given as pi r squared. Okay, it's given as pi r squared, which is giving us this. We know the radius is simply half of the diameter, therefore we get 1 millimeter squared, and in meters it's going to be 1 times 10 to the power minus 3 squared. So we have our area as 3.14 times 10 to the power minus 6 square meters. Okay, so now that we know our area as well as the force being applied to the ends of this wire, we can proceed and find the value of the stress that is applied to this wire. Therefore we say stress equals the force, which is 20 newtons, over the area of the wire. Okay, and we're getting stress as 6.37 times 10 to the power 6 newtons per square meters. Okay, so that is our stress. So now we go ahead to finding the strain. We know that strain is given as the extension over the original length. Therefore, we have that strain equals extension over the original length, knowing that the extension is 0.24 millimeters, and we convert that to meters, giving us 0.24 times 10 to the minus 3 meters, and the length was given as 4 meters. Okay, therefore we have that strain equals the extension divided by the original length, giving us the value of 6 times 10 to the power minus 5. Okay, notice here that the units are cancelling. We have meters for the extension as well as meters for the length. So this one here behaves like just a ratio without units. Okay, so let's move on. How do we find the Young's modulus? So the formula for obtaining the Young's modulus is given as Y equals stress over strain. Okay, we know that stress is force over area, and also strain is extension over the length. Okay, but since we have both values for the stress and the strain, we are simply going to substitute into this formula, giving us the Young's modulus equals the stress, okay, divided by the strain. Therefore, Y equals 1.06 times 10 to the power 11 newtons per square meters. Right, so this one was straightforward because we are simply using those formulas that we already know, and we substitute the values that were given in the question. Okay, so let's take a look at question 2 here. Question 2 here is saying a 15 kilograms mass fastened to the end of a steel wire of unstressed length 0.5 meters is whirled in a vertical circle with an angular velocity of 2 revolutions per second at the bottom of the circle. The cross-sectional area of the wire is 0.02 square centimeters. Calculate the elongation of the wire when the weight is at the lowest point of the path, given the Young's modulus for steel as 2 times 10 to the power 11 pascals. Okay, so the diagram may look like this. Okay, we have this mass which is fastened to a string and it's being whirled in a vertical circle. Okay, the circle being this, okay, being this direction like that. Okay, so now we want to find the elongation, or rather the extension of this wire when the mass reaches the lowest point of this path. Okay, so the first thing we should note here is that since this mass is going in a circular path and it's fastened to a central point, therefore we know that there is a centripetal force acting on this. Okay, and also there is a tension in the cord, therefore we are going to have a net force with the tension and the centripetal force. Okay, so let's take a look below here. We are saying that the net force here is going to be the centripetal force, because when it reaches at the bottom, the centripetal force will be acting upwards and also the tension will be acting upwards. Therefore the net force equals centripetal force plus the tension in the cord, giving Fc plus mg. Okay, but we know that the centripetal force is given as mv squared over r. Okay, therefore our net force, or rather F, is going to be mv squared over r plus mg. So we can pause here and we take this as our equation 1. So the reason for pausing here is because we have one unknown in this formula. If you look at it, of course we have the mass, we have the radius, okay, but we do not have v. So let's pause here and find a way of obtaining the value for v. We know that the angular speed here that we're given is omega equals 2 revolutions per second, which is equivalent to 4 pi radians per second. Okay, you can do that conversion just to confirm as you are solving. So we also know that the linear speed therefore is given as the angular speed multiplied by the radius, and the radius is 0.5 meters. Therefore we have 4 pi times 0.5, giving us a linear speed of 6.28 meters per second. So now that we know the value of v, we can go back to equation 1 and find the value of F. We simply substitute these values. We have F equals the mass mv squared divided by r, okay, plus mg. All right, so we have our mass as 15 kilograms, we have our v there as 6.28, and the rest are given in the question. Okay, so when we substitute those values, we're going to obtain the value of F as 1330 newtons. Okay, so this is the net force that is exerted on this wire. Okay, then also we have to take note of the area of this particular wire. A equals pi r squared, but this value is already given as 0.02 times 10 to the minus 4 square meters. Okay, So make sure if you're given the area in terms of millimeters, you have to take it back to meters, because that is the standard unit in this case. Okay, otherwise you are going to be finding wrong figures, okay, or wrong answers, so to say. So now we proceed. We know that the Young's modulus is given as force over area divided by change in length over the original length, or simply said, the stress over the strain. Okay, so from this expression we're able to find an expression for the change, or rather the elongation of this wire. We make the extension, or rather we find an expression for the extension. We are going to have the extension or elongation equals length times the force over Young's modulus times the area. We know the length, we know the force, we know the Young's modulus, and we also know the area. So we simply substitute the values. We are going to obtain this, and then have our elongation as 1.66 times 10 to the minus 3 meters, which is the same as 1.66 millimeters. Okay,